Hello, thank you very much for inviting me here. I am a postdoc over at the University of Amsterdam, and until about 2.5 months ago, I was doing my PhD at University College London. Just before the talk, I would like to acknowledge Philips, who now fund me, and Fight for Sight, who are a charity who used to fund me. So, thank you. Okay, cool. So, what am I going to be talking about today? I'm going to be talking about convolutions. Convolutions are pretty much at the center of this field of convolutional neural networks, which is, some people might argue, sort of the fuel behind this sort of deep learning revolution, or this AI revolution that's kind of taken us by force at the moment. And so I'm going to be looking at why CNNs are special, and it's got to do with convolutions. And then, after I've talked about that, I'm going to be talking about this idea, this sort of mathematical idea of symmetry, which is what convolutions are based on. And then I'm going to be trying to introduce a bit of mathematics, not too much, I promise, on these things called group symmetries, and then how we can then use group symmetries to generalize the convolution to other forms of transformation. And then I will talk about another way to do exactly the same thing, called harmonic or steerable convolutions, and then I'll sort of round up and sort of focus on the future. So let's get into it. What makes CNNs so special? They are pretty cool. They've got a lot of really nice applications. For instance, there's this one here, which is pose regression. So you're trying to localize the joints of a human being. And then from that, you can infer a skeleton. And this was a really nice paper at CVPR last year. They can also be used, and you guys should probably all know generative adversarial networks. They can be used to generate images like this. These people have never been seen. None of them exist in the real world. At least according to NVIDIA, they don't exist. And these were generated by adversarial networks. And then this is some work from the lab I was in, so Gabriel Brosto's lab, where they were doing something called monocular vision, or monocular depth estimation, sorry. From a single input image or video, you can estimate the depth of every single pixel in that image. And that's not a trivial task, because usually we estimate depth using 2 eyes. You need 2 images usually at least to be able to estimate depth. And this has applications possibly in the sort of self-driving car scenario or some other scenario similar to that. And CNNs have also been great in sort of image recognition tasks, such as this is the ImageNet recognition task. There's about 1.28 million images in this task, and this shows the error rate of classification in sort of what's called top 5 error in this classification task since 2011 to 2016. I couldn't get last year's numbers, so if you kind of look around 2011, we've got about 27% error rate, and now we're at, what, 3%, which is staggering. And all of these things that we can do are based on CNNs, which I think is very motivational. So what exactly is a CNN? So let's sort of take a step back and look at multi-layer perceptrons, which are sort of these fully connected neural networks. So there are several layers of neurons, and each neuron is kind of like a little computational sort of unit, and it looks at a previous layer of neurons, or at the very beginning of the network, it looks at, say, pixels in an image, or features in some big feature vector. And each neuron is connected to every other neuron in the layer before and after it. So they have this thing called global connectivity. But they're not really used in computer vision. And the reason is they kind of lack a few assumptions about how images work. So one thing which so a guy called Yann LeCun changed back in, I think it was either the 80s or 90s, kind of around that time, was the introduction of local receptive fields. So basically what this means is that in an image, I'm only going to connect my neuron to a very small patch, sort of localize where that neuron is placed. So we have a kind of a bed of these neurons spread across the image, and I'm only going to connect my neuron to the patch of pixels very close by to it. and then all of the weights connecting my neuron to my input are basically going to be replicated for each neuron in this sort of translational fashion. I'm just going to, there's another slide on this if you missed this anyway, so I'll just move on. And this is the basis of many state-of-the-art models, convolutions. So let's look at this a bit more. Why do we want local receptive fields? So I've got an image here. Oh, I can't. Oh, never mind, I can't use my clicker. Is there a pointer, by the way? I think there should be. Oh, this is it. Yeah. Perfect. Ooh. Excellent. Cool. So this is my image here. And there's a really interesting property of images, which is that if you take the correlation between pixels at some offset from each other, and then you normalize it and average it across all pixel locations, then you get a curve which kind of looks like this, where we've got pixel separation along the bottom and normalized correlation along the y-axis. And so basically, pixels which are further apart from each other have less to do with each other. They're less correlated. And so it doesn't really make sense to have a neuron which looks at pixels on one side of an image and on the other. We call this the locality of pixel statistics, and it's a property of image data. It's kind of interesting how this just arises naturally. The other thing, which is this translational wait time convolution, basically is related to a property of what we're trying to do, so which is classification. So this guy on the left, this is a doggy. This is also a doggy. You guys know that trivially. But a computer doesn't know that this and this are the exact same image, just translated. A computer just sees pixels. Pixels and more pixels, but in a different configuration. And so CNNs have this property of translation invariance, or actually I'm going to refine it a bit later to something called translation equivariance, built directly into them. But from classification, what we want is translational invariance. And this is a property of the task that we're trying to do. So convolutional neural networks aren't actually the best model for every task, but they work really well for classification and a couple of other things. So what is symmetry? So convolutions will tie into symmetry. I'll try and cover that in this part. So here's a mathematical definition. If I have some kind of function, this might be a feature extractor, a CNN, a convolutional layer, you name it, and it takes in an input image I, we say that f, this function here, is invariant to a set of transformations, which I'm going to label as this sort of curly t sub theta, if it basically ignores them entirely. I've got a function, an image, input transformation. And just a notational aside, some people don't really like this notation, so I'm just going to expand it a bit. So this might be some sort of translation. So T basically is an operator. It takes in an image and it spits out a new image. And so what this does is it spits out a translated image in this particular scenario. It depends on your interpretation and how you define it. And this will basically, when I look in at point x, it will actually return the value of the image, which is translated by theta at point x. We might have a rotation where we just replace the transformation, which was negative theta here, by some rotation operation. So usually we do that with a rotation matrix. Or pixel normalization. This isn't a geometric operation. This is a pre-processing step, which a lot of people do. So they take that image, they might subtract the mean of all of the pixel values in the image and divide by the standard deviation. This divide dot means sort of repeat this property element-wise. So repeat this for every single pixel. And there's no sub theta on here because basically mu and sigma in this particular case are functions of the image. So symmetry. We normally say that if a function f is invariant to a set of transformations theta, or t theta, we might also say that t sub theta are a bunch of symmetries of the function. So there's kind of two ways we can talk about this, invariance or symmetry. Basically, just think of them as the same thing. And examples of cases where we might want this are classification, quite trivially. We want to be invariant to translations, rotations, affine transformations, color transforms, contrast transforms, illumination, viewpoint, etc., etc. This is kind of like computer vision 101. Obviously, if you translate something so far that's off the side of your image, you can't really be invariant to that. Disentangling, this is another example. I've got a bunch of, so there's this famous problem called the cocktail party problem in machine learning. I have lots of people at a cocktail party, and they're all kind of nattering with each other, and then you put a microphone in the center of the room, and then you try and figure out what everyone's saying. It's just a hubbub. So what you do is you try and disentangle all of those signals. So you can have like speaker 1, speaker 2, speaker 3, all sort of neatly sort of laid out. And this problem is, it should be invariant to speaker identity. And so that's another case where we want an invariant problem. We also want it to be permutation invariant, actually. If I replace speaker 1 with speaker 2, kind of transpose their positions, it should also be the same. That's also a valid answer of my problem, valid solution. Another example is signal discovery or detection. So this is stolen, I forgot to put a reference here from I'll do the reference now, by a guy called Carl Kramer, who's at NYU. He gave a really nice talk at the NIPS conference a few years ago, where they were talking about applying machine learning to discovering signals in the LHC. And you could imagine, so this is kind of a little pizza segment from a big circular detector, and it shouldn't really matter exactly which segment you're looking in, assuming you kind of ignore gravity. If you have a sort of a particle traveling from the center outwards, it shouldn't matter if it sort of takes this path, or a path like this, or a path like that, or a path like that. If it's there, you want to be able to detect it. So I think everyone kind of gets the idea of symmetry now, hopefully. So we talked about invariance, which is sort of summed up in this equation here, but there's something called equivariance, and this is where convolutions come in. And equivariance is a slight modification or a generalization of this function. So, of this equation, sorry. So here on the right, I've got some transformation t, and now I've introduced a transformation s of theta. So basically what this equation is saying is an equivariant function is one where I could take an image I could then transform it via t, and then pass it through my feature detector. Or I could have equally taken my image, passed it through the feature detector, and then transformed it in the feature space. And those should give me the same answer. And not all functions satisfy this property. But functions which do satisfy this property they have some really nice properties which make them really easy to work with. So yeah, here we are, transformation in feature space. And these are basically kind of the same transformation, but in different spaces. But be warned, they don't always mean the exact same thing. So invariance is basically when you take this operation here to be the identity. So this is what mathematicians might call a homomorphism. So you might have, say, all translations of my puppy face in this image before going through a CNN. And then if I want invariance, it might just be that I can't regain any of that sort of translation information or rotation or whatever information from the feature space directly. Convolutions serve this, are equivariant. So this is my notation for a convolution. It's this star thing. Well, technically what I really mean is correlation, but seems that machine learning people prefer to use the term convolution. And correlation is basically, I've got an image, I've got a filter, I'm going to scan my filter across this image lots and lots, and then I get a set of responses. And that could also be seen as a linear transformation going from this image to this sort of receptive, this set of responses, but where I've tied the filter weights translationally between each position. And this is really nice because if I get my input and then I shift it, so like 5 pixels to the right, the activation should also shift 5 pixels to the right. So that is an equivariant transformation. Another one is the Fourier spectrum phase, which I'll talk about later. Yeah. And so the really cool thing about equivariant transformations is that they preserve the structure of transformations that we're interested in. They preserve the structure of translations, rotations, etc., etc. And this is really useful if we want to sort of get a real good handle on how images transform in feature space, or how feature representations transform given images. Just a bit more on equivariance. Not everyone gets this. I mean, I did this for my PhD, which was 3.5 years, and it only took me about 3 years until I realized this property. So I think this is quite useful. Someone pointed this out to me, Andrew Vidaldi. I'll just thank him at the bottom there. So this is, again, equivariance again. I've got an input space, a feature space, function connecting the two. I've got an input point, blast up into feature space. I then transform the the image, take the features of it. Equivariance says I could go down this path or this path. If I take another input, and it just so happens that this input maps to the very same point as this one over here, then an equivariant map says if I then transform the input, the secondary input, and then took it into feature space, it must end up at the same point as this point. So these 2 points must also be the same. So when 2 points end up at the same point in feature space, they're said to be in the same equivalence class. And equivariant functions preserve equivalence classes. So this is a kind of invariance, in a way. It preserves the fact that if these two input points end up in the same feature, there is some sort of transformation I could draw between the two, which makes this mapping F invariant to that transformation. And so it's always invariant to that transformation. Equivalent classes are preserved. And so the whole task of machine learning, you might say in the computer vision domain, can usually be boiled down to finding feature spaces which are equivariant to chosen transformations, or if you're really lazy like me, to learnt transformations. And so here's an example where we just took, I think it was like either the third or the fifth layer. It was definitely an odd one, if I remember correctly. And we fed in this little boy on the left and rotated it and looked at the features. And this is what the features look like. We then got a little square and we rectified it. And this is what the features look after you rectify them. And the pixel locations, the activations at the pixels, they change in intensity, which means that the activations change as a function of the little boy's rotation. And that's kind of cool. So there's probably some sort of equivariance going on there. But we don't really know exactly what that equivariance is. We don't know how these pixels will transform as a function of this little boy going around. Because it might depend on the input as well, like what texture you're seeing. So the question is, can we just design a really obvious transformation into the network, an obvious equivariance, you might say. And to be able to do that, we just need to understand a bit more about symmetries and a bit more about transformations and like how they work. So this requires a bit of group theory. I was not a mathematician in the start, so I like to explain things with pictures quite a lot of the time. I suppose it's probably quite idiosyncratic of computer vision people. And so group theory is this sort of abstract field of mathematics, and it's just a language, you might say, to describe invertible transformations. It is also a language which describes a lot of other things. Just want to sort of put a caveat out there for all of the abstract mathematicians out there, or physicists. But it's really useful for describing invertible transformations. So one of the properties of a group is that it's closed. And what this means is that if I take an owl, a picture of an owl, and then I apply some transformation to it, like a right-angle transformation, and then I take another random transformation in my set of transformations G, and I just apply this on to the transformed image, then basically 2 rotations should also be a rotation. That should be kind of intuitive, hopefully. So no matter what combinations of rotations I take, I should always have a rotation. And then there's this other property called associativity. This is just more of a mathematical sort of thing which makes everything nicer to work with if you do the maths, which is basically if I have a bunch of transformations. So here I've got this notation where I use these t's. And I forgot to kind of do that in the left-hand side, but imagine instead of like T and H, I've got these, sorry, G and H, I've got these T sub G's, T sub H's written on the left here. Just imagine there's a T above the letter. Basically, it says I can kind of do a set of operations and I can kind of bracket them in different ways. So I can run them in sort of slightly different orders. I can evaluate either the first operation together and then apply the second operation, or I could create a new operation from these two G and H's here and then concatenate it on the end of K. And if you look at this sort of this flow of transformations here, what that's basically saying is I can say, if I take H and K together, that's the same as doing this and this together. So that's, I could just, instead of doing two 90-degree rotations, I do a 180-degree rotation, and then a 90-degree rotation, or I could do 90 and then 180 degrees. It's maybe it's not much point to go into that too detailed. And then there should be a do-nothing operation and invertibility. So if I have an hour and then I rotate it, I should also be able to go back. So this only works for invertible transformations. Examples are translation, and you can prove this to yourself in your spare time. Translations of translations are translations, etc., etc. I can always invert a translation. Rotations, the same. Roto-translations, which are rotations and translations sort of built in with each other, sorry, mixed together. So this guy here is kind of moved up and then rotated. I suppose you could also sort of rotate and then translate. Reflections. Scalings. There's actually different ways to model scalings. You might model them with a group, but I put a little sort of star down here. It's probably better to model them with something called a semi-group, which is basically like a group without that invertibility condition. And it's also without the identity condition, but that's more of a technical detail. A non-example is occlusions. So you've got little birdie in a book. Birdie walks behind the book. You can't invert this operation because I don't know what the birdie's face looks like. So now that we've looked a bit at groups, we can talk about these things called group convolutions. And essentially, this is the formula of a convolution, normally inside a neural network. I've got an image, I've got a kernel, and I translate the kernel by some amount y, take the inner product, and that gives me the convolution response at position y. So here's an image. It's got 4 pixels, and here's my kernel, my filters w. I take the inner product at 4 locations, 1, 2, 3, 4. So you can kind of see why that works, because you've got 4x4 filter here, sorry, 4x4 image. You've got 3x3 kernel. So you can only sort of, you could take the kernel in the top right position and take the inner product there, or you could move over 1 pixel left, 1 pixel down, or 1 pixel down and left. And those are the only sort of inner products you can do, which will give you a response like this. Now, if I were to move my input image to the left inside this image here, then my response would all move left. Down and left, and down. I'll just wait for people to finish taking their photos. Cool. Right, so that's the standard convolution, and everyone hopefully should about know that. Now, I'm just going to jump into a group convolution by example. And a group convolution is a generalization of a convolution to other kinds of transformations. So, like rotation, for instance. So, in here, beforehand, so this is the reference from last time, we got our kernel and we translated it. Now we're getting a kernel and we're rotating it. The -1 here, by the way, is just convention. And then, beforehand, what we did in the convolution, we indexed by the translation, y. Now we index by the rotation. So this is the part where you start needing to think, hopefully. So everyone just pay attention for 5 minutes, then you can go back to sleep. What I take is my image, and I've kind of repeated the image down here on the left. And then what I do is I take my kernel, and I take the kernel, I rotate it by 90 degrees, 90 degrees again, 90 degrees again. 90-degree rotations is just a very simple example. Works really nicely on a square lattice as well, on a grid. And what I do is I take the inner product of this patch on the left and this kernel here. That's basically this where theta is equal to 0. So this is just simple inner product. And that gives me this red response. And then I go down to my next theta, so theta of 90 degrees, take the inner product, that gives me this blue thing. Again, the light blue thing. And then when I've done, was it 270 degrees, rotation of my W, inner product of I, that gives me the yellow thing. Now, the really fun stuff happens when I start to transform my input, I, which is my image. So now what I've done, hopefully you can all see this, I've taken I and I've rotated it by 90 degrees. And what's happened is that it shifted the responses cyclically. So the red pixel has moved down in my response. And I've drawn them in a vector just because it's a bit easier to draw. The red has moved down, and so is the blue, so is the light blue, and then the yellow one has kind of popped off the end and gone back on the top. And this works because you can kind of imagine the relative positioning or the relative rotation of the image on the left here and this kernel here is exactly the same as the relative sort of angle of this and this here. So transforming the left thing, the image, will transform the output. And then when you keep on applying this transformation of 90 degrees, this then shifts down and down and down. So now we have a way to define convolutions over rotation, which is kind of cool. And in the hidden layers, let's probably just go read the paper. It's probably a bit easier to understand what happens in the hidden layers. Right. So now we can go on to ROTO-TRANSLATION. So ROTO-TRANSLATION is basically translations and rotations in sort of one unified group. So the ROTO-TRANSLATION convolution looks a bit like this. And now, I lied a bit. You guys have to really think for this one. This is my image. I haven't drawn all the different kinds of possibilities of rotating and translating my input kernel. But if I did, this is 4 by 4. I've got a 3 by 3 kernel. There are 4 rotations of the kernel, and there are 4 translated positions I could put them in. So there should be 16 activations or responses up here. And I've done this correctly, so there are. Going down this side should give you your theta dimension, and these two give you kind of your offsets y in the two directions, your x and your y in a way, you might call it. And so what happens when I rotate my input? Well, what happens is that the responses corresponding to this bottom right sort of column here, if you could imagine it, like when I rotate my input, spatially what's going to happen is that the responses are actually going to rotate in space. And so the responses rotate from this column here to this column here. At the same time, we've got that rotation convolution going on in the background, which permutes all the positions of these pixels, of these responses. So what happens is that this red thing has gone across one, and then it's moved down because of this permutation. And the same for all the others. And if I repeat that, this should be 3D. This red pixel again has gone down, and then down and around the back. So what happens is that as you rotate the input image, these responses are kind of making this corkscrewing sort of pattern through space. And that's kind of that really screws with your mind. It did mine for quite a long time. It's probably why I'm still in academia. Yeah, so that's the ROTO-TRANSLATION convolution. And so these things are really cool. They allow us to do lots of really nice things with respect to giving guarantees to how our neural networks perform when I translate images or rotate them. And so I've given sort of 3 examples. You've got your standard convolution, your rotational convolution, and your ROTO-TRANSLATIONal convolution. But they all sort of sit into this one framework, which is that if you look here, what I've done is I've changed the transformation I've applied to my kernel. And so I could rewrite that as this transformation operator, which I introduced earlier. So a group convolution is basically a convolution where instead of translating the input kernel, I transform it in some way. and you define what T is. T of theta has to be an operator from a group. So I cannot do occlusions or blurs or more funky things like that, which are non-invertible. And there's an equivalent, oh, sorry. Whoops. And the thing to remember about this is that what you do is the response of a convolution is indexed by the transformation parameters. And there's an equivalent version for hidden layers. And, oh, yeah. So there's a paper, if you're interested in this stuff, you should read this paper, Group Equivariant Convolutional Networks by Cohen and Welling. And they're the ones who sort of outlined, they introduced this sort of entire framework. But they only did it for discrete transformations at the time. Here's some examples. So, as I said, I moved to University of Amsterdam. In my lab, which is the Philips lab, there's a guy called Bos Veiling. And Bos has applied these group equivariant CNNs to histopathology sort of screening. And so what we have here on the left is a slide from a histopathology slide. And then we're predicting, I really apologize, I actually cannot remember what we're predicting. I think we're predicting sort of the presence of tumors. We've got the mean predictions for a classical CNN and then sort of a rotation equivariant one. So actually ROTO-TRANSLATION equivariant, sorry. And then we've done some Bayesian stuff on the right. But this stuff is less interesting from the point of view of this particular talk, but it's always nice. And the really cool thing is if you look at, so FROC is just a measure of performance. If you look at what happens when you decrease the amount of data that you train your network on, what happens is that PM4 DenseNet, that's the roto-translation equivariant one. DenseNet is just translation equivariant. The blue column is always a bit taller than the orange one, and this difference gets more so when you have less and less data. And the reason for that is that the networks, in very hand-wavy terms, networks know that if I feed in two different images, which are exactly the same in nature, but they are transformed versions of each other, they are exactly the same thing. Normally with a CNN, you have to teach it to understand that in some sense. But these ones just know, it's built as an inductive inductive bias, we say. Another example, something I pushed out a few months ago, CubeNet, we basically do roto-translation in 3 dimensions. 3-dimensional rotations are actually fairly complicated. They are what's called non-commutative. So if I do transformation, so rotation A followed by rotation B, that's not the same as B followed by A. And this big sort of colorful thing is just a sort of a lookup table called a Cayley table. If I've got, say, 24 different kinds of right angle rotation I could do on the left, and if I concatenate one with the other, I should end up with a third transformation. This is just a lookup table to say, if I take rotation 10 and rotation 23, then I end up with rotation, I think it says 19, but I can't quite tell, or 9. Anyway, the bottom line is we do fairly well with this sort of thing with very little data. We were actually beat by one paper, but they had, rather than just one, they had 6 networks, and they trained for like a month. And I think they had lots of money, so join us instead. Right, so we looked at all of that kind of sort of discrete transformations, but we live in a very continuous world. So some of my PhD was sort of looking at how do we model continuous transformation side neural networks. And this is where the harmonic, or what's also known as the steerable convolution, comes in. So rotations are kind of where it's at the moment in the state of a field. So I thought I'd collate a few different papers. So in some papers, what they do is they rotate the filters by, so there's a whole load of different papers which, whether they know it or not, are basically doing group convolutions. And some of them rotate their filters in that convolution. Some of them will store the entire response, or they'll take the max and the mean, and there's a few more which are published later. Some instead will actually rotate the activations instead of the kernels. Some instead also just rotate the input, but do nothing to the CNN at all. These are some older papers. 2016, by our standards, is old. And then there's some sort of newer stuff where They do some special coordinate transformations, but these things can only deal with global transformations rather than sort of local deformations of the image. Oops. But they all deal with discrete transformations. So one way to look at continuous transformations is there's a rule called the Fourier shift theorem, and this is really beautiful. So this thing is called a Fourier transform, and basically it looks like an inner product, or it's basically an inner product, between a function, and this is defined on the circle in this particular case, and some other function. So this is my image, and this is some sort of kernel, for instance. And this is a complex exponential, so e to the minus. I use iotas instead of i's or j's, because I did engineering to begin with, and I always write the complex, like the negative -1 with a j, and that really annoys all of my colleagues who use an I, but I can't use an I, so I use an iota. So I've got minus iota, and then there's an m phi. M is a discrete number, which is basically frequency. There we are. And so what you can do is you can actually just do a little change of variables. It's kind of like GCSE mathematics, and then you can separate this exponential, which might be A-level mathematics, I think. And then what you basically see is that what you end up with is a part which is not dependent on theta. So, sorry, I should backtrack a bit. What we had was an image I rotated by a certain amount theta. And what we've done now is we've actually been able to pull the transformation theta outside. And so there's this invariant part which just depends on the image content, and this equivariant part which depends on its phase or its rotation. And this is really, really neat. And so what this looks a bit like to me is a bit like a convolution, but where I've just taken the convolution and indexed it at a particular angle. And yeah, this Fourier shift theorem actually generalizes beyond 1D transformations to groups. And so basically what we end up doing is we can define a convolutional neural network where we replace the normal filters with filters which are constrained in this axial direction, the angular direction, sorry. And so they're constrained to have this sort of angular part, and then they have this free part which is sort of defined in the radial direction. And they don't interact. So this thing we can learn, this thing is constrained. Radial part learn, angular part learn, not learned, defined. And here are a couple of examples of what these filters look like. This thing is complex, so it's got a real and an imaginary part. And depending on what m is, we get different frequencies. So m equals 0 is kind of invariant on the circle. M equals 1 is a single sort of sinusoid. M equals 2 is sort of higher frequency. Right. And then just in practical terms, we can, actually I can just skip this, it's probably not so interesting. But maybe the bottom part is, because we've now defined images and kernels as being complex valued, because we've got these exponentials, which are complex exponentials, what we can do is when we actually implement this, it just turns out to be 4 normal convolutions, 4 real convolutions. So that's just a 4 times sort of complexity increase. So it's a constant factor. So it actually doesn't change the computational complexity of our algorithm at all. And so just to sort of to recap on that math with a nice diagram, what we've got is we've got an image, which might be this k here. So now it's the image, it's got radial position r and angular positions phi. And now if I take the inner product with, oops, okay, where are they? Yeah. If I take the inner product of that image with one of these guys, and one of these guys it's always a pair, then I get a complex number out, which I can denote as a vector. The length of this is that invariant part, which says like how much is this feature here, and the angle tells me the orientation. If instead I'd originally transformed my input and then applied my complex inner product, what would happen is that this feature, this vector would have rotated anti-clockwise by an amount m theta, where m is the frequency of the input kernel. So in the same thing, it's got the same length, but a different phase. And then I could have gone this way as well. So this is this lovely equivariance sort of square, which we always see. And this is an example of one of these filters applied to, like I say, a number 8. What you get is like different, so this one's sort of like edge seeking. It gets different magnitudes on the edges and far away from the edges, but also different directions. And so this is a very rich encoding of the input space. And one of the cool things is if you sort of do a convolution with one of these filters, we can define nonlinearities on that. I won't go into details. If you then chain it with another convolution, so convolution 1 has frequency m1, convolution 2 has frequency m2, then the, oops, did that not show? Oh, whoops. Anyway, the frequencies sum. The frequencies, this is the equivalent to doing a convolution with a different filter, which kind of looks like a frequency m1 plus m2 filter. But it's not exactly the same. I might be the next slide, sorry. So again, I've got my input image, it's a cat. I've taken convolution with frequency 0, 1, and 2 filters. What happens next? Ah, here we are. Sorry about that. I've taken my image and I've convolved it twice. If I were to transform the input, then what we get is a rotation of the original response by e to the iota m1 plus m2 theta. So what exactly does that mean? So I've taken a convolution and I apply another convolution of different frequencies. So this is kind of 0 followed by 0. This is going to be frequency 1 followed by -1 to get back to 0. Frequency 1 followed by 0, frequency 1 followed by 1, or just frequency 2. So if I take convolution of, what am I doing here? If I were to, so let's go back to this diagram. Exactly what this is I've taken the convolution of this input image with a filter and then convolved with a bunch of other filters and then just summed the responses from various responses at this point here. And then if you're not careful, what happens is that you get this kind of action. When I've taken my input image and rotated it, and I look at the response, I get this horrible thing here, which I cannot infer the input angle from. And basically what's happening is you get this thing called interference. So we came up with this equivariance condition or coherence condition. So essentially what we say is if you follow a set of convolutions at a single channel deep in my network, I've got to make sure that the sum along all the paths of convolutions are always the same. So if I go from my input to where I am, and then the sum of all of the convolutions, those frequencies, was 2, it should be 2 no matter which path I take. Otherwise, equivariance just breaks, or linear equivariance just breaks. It's probably one of the more complicated ideas. But basically, there's a constraint on the way how we can connect these things up. And then the nice thing is we can then sort of always convolve things back down to this 0 frequency, sort of we call it a stream, or 0 frequency filter, or response, which basically is invariant to input angle. And okay, and so this is the harmonic network. We published this last year at CVPR, and had a very nice time in Hawaii. And yeah, people like the paper, so it's nice. So where does it take us? So we tried a couple of experiments, a really tiny experiment we just did. Everyone uses MNIST apparently in this area. So we tried this on MNIST, and there's a rotated version. And what we found was that like these discrete rotation networks, we can get good accuracy at small training set sizes. So this is like sort of 12,000 all the way down to 2,000. And if you normalize the test accuracy, a normal CNN is the blue thing. A CNN trained with data augmentation is the green thing. And our thing is the red thing. And this was really striking. The fact that even if you show your CNN images at all rotations to start off with, and so you train, and this is the usual way how people learn to be invariant to certain input transformations. Even with that, we can still do better, which I thought was really cool. I'm guessing we probably just didn't fine-tune this enough, but then you need so many GPU hours, and who really cares about MNIST? There might be people, I don't know. And so another thing we tried was boundary segmentation, and so this is a standard sort of network that people use. You've got these convolutions, which are in red. You've got these blue things, which I think were max pooling, or mean pooling. And then the particular network we used was called a deeply supervised network. And so what happens is you take a one-by-one convolution, every second convolution, which is this green thing, which collapses all of the image information into a single channel, which is this one thing here. And then you stack all of these things up. So at resolution, so at the sort of the input resolution, half of it, half of it, half of it, and half of it again. You stack all of these things up into one image, and then you do another one-by-one convolution on top. And then hopefully you should be able to get images like this, which give you boundaries of images. And this is useful, say, like if you've got like a robot which is kind of trying to find its way through a landscape where it's never seen any of the objects in that landscape before. So yeah, someone's always sort of said to me, like, oh, why don't you just use sort of like semantic segmentation? So semantic segmentation is basically where you associate a class with every single pixel. Well, that only works if you've seen this scene before. If you know what a car is, if you know what a pyramid looks like, or a camel, if you've never seen one of those things, then boundary segmentation is a great way to kind of get a rough idea of the geometry of the scene you're living in. And then we made a harmonic version, and we trained against things which weren't pre-trained on ImageNet. And yeah, bold numbers as usual. Someone once said to me, they're kind of sick of computer vision nowadays because it's all about just getting the bold numbers in the big table at the end of your paper. And yeah, and look, somebody else recently, using an equivariant network principle actually got slightly bolder numbers than ours, but this was more recent. And one of the cool things is because we've designed everything with these phases inside the network, we can just pull out orientations automatically. So this kind of wheel encodes orientation. A master's student pointed out to me it's kind of off slightly. I didn't rotate it properly, but the basic idea is you can kind of pull out an edge and an orientation. And this is useful because you kind of, a lot of the time you want to know which side is out and which side is in. And so let's go back to this little boy's face again. And what we've done now is we've taken the same layer as we did in the VGG network. We've registered the features, and then we've just taken the magnitude part because it's invariant to the input transformation, and this is what we have. If I do a side by side, this was the VGG on the left, and this is us. So we're not perfect, but I think we're doing a bit better. As you can see, there are some artifacts here which we think are due to discretization. But on the whole, I think it's getting there. Oops, whoops. So I'm nearly at the end. Oh yeah. I'm going to talk about the future. So I'm going to sum up and talk about the future now. So GCOMs are just a shorthand way of talking about these discrete group transformations. And it turns out we've just been doing lots and lots of experiments to just try and compare like sort of these harmonic networks and these discrete group convolutional networks. They've got great discriminativity, but they've kind of got okay equivariance. So because they're only being equivariant, they're invariant to discrete transformations of your input. What happens between a 90-degree rotation? You kind of just have to, you still have to use data augmentation to be invariant for transformations between those angles or other kinds of transformation. On the other hand, harmonic networks have got really nice equivariance properties, but because we're using these Fourier-like circular harmonic filters, which are very limited in their discriminativity, the entire network together doesn't really have very good performance in, say, classification, but it always gives you the same crappy output, no matter what angle. And so there's a couple of things we need to work on still. These networks don't really have a good sort of generalization theory yet. Although a guy called Tucker Cohen, who came up with the GCOMs, actually sort of said these two things, he's written a paper now, which says that these two things are actually, in some sense, equivalent. They fit into a unifying theory. And so we can actually treat both of these things as the same thing in a sense. And so more personal questions for me are like, is group theory too restrictive? I think it is, because you have to limit yourself to transformations which are invertible. Scalar transformations in general are non-invertible. If I take an image and I reduce it to like half of its size, I get rid of a lot of the pixel information. I just discard that information. I cannot invert that operation perfectly. If I'm standing in front of you guys, I live in 3D, but you guys see a 2D projection of me. If I now turn on my side, the information from my cheek on this side away from you, you cannot see that. You can't invert this 3D rotation projection to a 2D plane. So we need something more than these group symmetries to take us to the next step. Oh, I said that. But even despite that, even despite the fact that there is actually theory on these GCOMs, we still haven't looked at things like scale. Well, actually, not scale, because it doesn't get covered by the theory. But there are other kinds of group transformation which have been covered. I'd just like to sort of end on this, and I'd like to thank my collaborators, Stefan Garbin, Daniel Turno-Kambatov, Gabriel Rostow, and Max Welling, who's my new employer. Thank you very much. So we've got time for a couple of questions if people want some. Yes?
Have you looked also into learning group transformations without specifying them beforehand?
Yes, so there's various approaches you can take to this. So there are ones where maybe you can model the transformations with a simulator, but you can't write them down in a closed mathematical form. There are a few papers on that, and I got one from last year as well. And then ones where you really just don't know what the transformation is at all, and you just want to discover them from sort of the data. As of yet, no. We haven't looked directly at that. That is a very big question. I think if you could publish a paper on that, you would be up there with the sort of machine learning gods. But that would be really cool to do. Hello? Yep.
Thanks for the talk. Very, very cool. So I have two questions. I have two questions. First question is basically, is it correct to say that you get full invariance over whatever angle the rotation you have in your image because of multiple layers basically summing up of your kernels, essentially? That's you mean the Gaussian kernels that you have on multiple layers, and they kind of sum up, as you said, and you get invariance over all the summed angles.
Yeah, so one way to get invariance is to take an equivariant output and to do a kind of a mean pooling on it. So you can get a convolution. So normally for translation, people will do these convolutional networks, and then at the very last layer, they'll do this thing called global average pooling, which is just taking a mean over translations, a mean in the spatial dimension. That gives you invariance. And you can define a similar thing for these group convolutions. Sorry, yeah?
Okay. So the second question was about the signal interference, essentially from multiple convolutions. So is it correct to say that you can probably regularize over the different weights of the convolutions on different layers to remove the interference, essentially to say that your network will be better invariant against certain kinds of rotations as opposed to all kinds of rotations equally?
So I think you might be, sorry, I'm just want to understand your question a bit more. Are you talking about when we're, I didn't explain this part particularly well. I'm guessing you want me to explain this in a bit more depth, or?
Maybe I can ask a question in private if you like.
Yeah, okay, sure. Yes? Yeah.
I was wondering about the computational cost of these microphones.
So the question was about the computational cost.
Because if you have a convolution, if you want to apply convolution on an image with, say, n pixels, you're effectively applying the kernel n times. So you've got, say, an order n operation plus any other.
Yeah, so it's dimensionality.
So if you're doing theta angles on top, doesn't that just make it an n times theta operation, or is there any way to?
Yeah, so there's kind of a trade-off. So you're increasing. So you could imagine this as taking a kernel and then just copying it at n angles and like h times w positions, spatial positions. What that means is, you have a higher amount of computation you have to do, but usually CNNs have to learn a lot of these transformations in the first place. And so what we found is that while you need more copies of the kernels, you actually end up having fewer kernels, because if you look inside the first layer of like AlexNet, for instance, you have the same filters at different orientations. And so we're just not learning those filter copies anymore, we're just copying them ourselves. But I think that is a very good question in terms of if we start going into all sorts of if we get like scale and rotation and translation and flips, etc., we are going to need bigger GPUs. But then some people might just say, wait 5 years and NVIDIA will have something bigger.
But in a sense, you said you were a bit surprised that you got better results than the augmented set. Isn't it fair to say that, in a sense, the augmented set is only trying a couple of orientations where you've gone through all of them?
Okay, so specifically with the augmented set, we were doing sort of random augmentations at training time. So we trained all of our networks for the same amount of time, which was many, many epochs, probably like 100 epochs, say. That's not the actual number, but I'm just, for instance. And then when we trained, every image got a random rotation between 0 and 2 pi. So you'd think that probably would cover it quite well. And it always seems to sort of converge anyway. So I think that's probably it. Hello, yes?
One last question.
Oh. Well, I'd already started, yeah.
I think I'm referring to similar questions to those just asked. But so one thing is you mentioned the advantage of the domain of images being smooth, 2 pixels being close together, having a correlated color. I take it that informs how you rotate the kernels later on when using them?
So you're saying that the...
You didn't mention explicitly, sorry, I'll state it as a question.
Okay.
You didn't mention explicitly how you use this property of images.
So this locality.
Yes.
Okay, so so it's kind of implicit. It's kind of it is there. So the locality of pixel statistics is used in the fact that our kernels are restricted to, say, 5 by 5 pixels, for instance. So they don't span the entire image. They're small kernels, but we copy them at lots of positions. Okay.
It's not so surprising that the augmented network, if it was the same number of iterations, performed less well, because it's just a wider model, right? Essentially, it could in theory match your model, but in theory also connected neural net could match your model. It's just much less.
In theory, yeah. I mean, this has happened time and time again. There's lots of papers on this specific kind of comparison, and they do show time and time again that the ones with equivariance built directly into them work a lot better than the ones where you just deal with data augmentation. And it might be to do, my hunch is it's probably to do with the optimizers that we have. Using these stochastic gradient descent optimizers, these first order optimizers don't really ever get you to a very good local minimum. So, yeah. Just a guess, though.
Thanks, Daniel.
Right.